Hello everyone, I'm Vikram P. Madduri here. I'm a software architect and welcome to Softech. And in this session, we're going to continue with the basic introduction about machine learning. That's a chapter one. Chapter one is basically all about the introduction about machine learning. And there's a part two session. So I already have done the part one and you can find it just below this video. Okay, so we are considering another scenario wherein we have a issue which is very quite quite we are quite aware of it. We can relate it to this particular scenario wherein, like, for a frequent traveler, emails from an airline informing him about the recent discounts might prove very valuable information, and whereas for many other recipients this might prove more of a nuisance because they're not interested as of now for traveling. So when the email relates to products available only overseas, so moreover the nature of annoying emails might change over time, example through the availability of new products like Viagra, Cialis or Levitra or whatever it might be. So different opportunities for fraud, the Nigerian 419 scam, which took a new twist after the Iraq War, or different data types, spams, which consists mainly of images. To combat these problems, what we have done is, like, we have done a binary classification. So we have, basically a seemingly unrelated problem that is of cancer. Okay, so we consider a particular scenario in which, we have a binary classification, separate stars from diamonds. So in this example we are able to do so by drawing a straight line which separates both sets. So we will set later that this is an important example of what is called a linear classifier. We want to build a system which is able to learn how to classify new emails. So basically this is a simple example wherein we have the stars and we have the the blocks, and the blocks represents something which is important, and the stars may not be important. So we just classify them based on a particular scenario or criteria. So a seemingly unrelated problem, that of a cancer diagnosis, shows a common structure. So given historical data, so example from a microarray analysis of a patient's tissue, infer whether a patient is healthy or not. Again, we are asked to generate a yes or no answer given a set of observations. So we will see that in the in a diagram. So it is useful to characterize learning problems according to the type of data they use. So this is great help when encountering new challenges, since quite often problems on similar data types can be solved with very similar techniques. For instance, natural language processing, that NLP, and bioinformatics use very similar tools for strings of natural language text and for DNA sequences. So vectors constitute the most basic entity we might encounter in our work. So for instance, a life insurance company might be interested in obtaining the vector of variables. So blood pressure, heart rate, height, weight, cholesterol levels, smoker, gender, to infer the life expectancy of the potential customer. A farmer might be interested in determining the ripeness of fruit based on the size, weight, spectral data. So these are two instances where we might have to use the past data and analysis. So an engineer might want to find dependencies in voltage, current, pace. Likewise, one might want to represent documents by a vector of counts which describe the occurrence of words. The latter is commonly referred to as the bag of words features. So one of the challenges in dealing with vectors is that the scales and units of different coordinates may vary widely. So for instance, we could measure the height in kilograms, pounds, grams, tons, stones, all of which would amount to multiplicative changes. So likewise, when representing temperatures, we have a full class of affine transformations, depending on whether we represent them in terms of Celsius, Kelvin, or Fahrenheit. One way of dealing with those issues is an automatic fashion is to normalize the data. So we will discuss means of doing so in an automatic fashion. So we have some kind of concept of lists. In some cases, the vectors we obtain may contain a variable number of features. For instance, a physician might not necessarily decide to perform a full battery of diagnostics tests if the patient appears to be healthy. Sets may appear in learning problems whenever there is a large number of potential causes of an effect, which are not well determined. For instance, it is relatively easy to obtain data concerning the toxicity of mushrooms. It would be desirable to use such data to infer the toxicity of a new mushroom given information about its chemical compounds. However, mushrooms contain a cocktail of compounds out of which one or more may be toxic. Consequently, we need to infer the properties of an object given a set of features whose composition and number may vary considerably. So matrices are convenient means of representing pair-based relationships. For instance, in collaborative filtering applications, the rows of the matrix may represent users, whereas the columns correspond to the products. Only in some cases, we will have to have the knowledge about a given user or a product, or a combination, such as the rating of the product by a user. So a related situation occurs whenever we only have similarity information between observations as implemented by a semi-empirical in distance measure. So some homology searches in bioinformatics, example in variance of BLAST, only returns a similarity score which does not necessarily satisfy the requirements of metric. Now, images could be thought of as a two-dimensional arrays of numbers, that is matrices. This representation is very crude, though, since they exhibit spatial coherence, lines, shapes, and natural images exhibit a multi-resolution structure. That is, downsampling an image leads to an object which has very similar statistics to the original image. So computer vision and psychopathics as well have created a raft of tools for describing these phenomena. So video adds a temporal dimension to images. So basically video adds a temporal dimension to the images. So again, we could represent them as three-dimensional arrays. Good algorithms, however, take the temporal coherence of the images sequence into account. Trees and graphs are often used to describe relations between collections of objects. For instance, the ontology of web pages of the DMOZ project, the www.dmoz.org, has the form of a tree with topics becoming increasingly refined as we traverse from the root to one of the leaves. So ads, animation, anime, general fan pages, official sites. This is what we have. So in the case of gene ontology, the relationships form a directed acyclic graph, also referred to as a GODAC. Both examples above describe estimation problems where our observations are vertices of a tree or a graph. However, graphs themselves may be the observations. So for instance, the DOM tree of a web page, the call graph of a computer program, or the protein-protein interaction networks may form the basis upon which we may want to perform the inference. Then we have the strings occur frequently, mainly in the area of bioinformatics and natural language processing. So they may be the input to our estimation problems. Example, when classifying an email as a spam, when attempting to locate all names of a person and organizations in a text, or when modeling the topic structure of a document. So equally well, they may constitute the output of a system. For instance, we may want to perform document summarization, automatic translation, or attempt to answer natural language queries. Compound structures are the most commonly occurring objects. That is, in most situations, we will have a structured mix of different data types. So for instance, a web page might contain images, text, tables, which in turn contains numbers and lists, all of which might constitute nodes on a graph of web pages linked among each other. So good statistical modeling takes such deep dependencies and structures into account in order to tailor sufficiently flexible models. Now coming to this problems, the range of learning problems is clearly large as we saw when discussing applications. That said, the researchers have identified an ever-growing number of templates which can be used to address a large set of situations. It is those templates which make deployment of machine learning in practice easy, and our discussion will largely focus on a choice set of such problems. So we now give by no means a complete list of templates. So binary classification is probably the most frequently studied problem in machine learning, and it has led to a large number of important algorithms and theoretic developments over the past century. So in its simplest form, it reduces to the question: given a pattern X drawn from a domain X, estimate which value an associated binary random variable Y belongs to plus or minus 1 will assume. So this is what we have. Now, for instance, given pictures of apples and oranges, we might want to state whether the object in question is an apple or an orange. Equally well, we might want to predict whether a homeowner might default on his loan. Given income data, his credit history, or whether a given email is a spam or ham. So the ability to solve this basic problem already allows us to address a large variety of practical settings. So there are many variants exist with the regards to the protocol in which we are required to make our estimation. So here we have a complex scenario where we have to categorize on a multiple criteria, and then we need to classify them as best as possible. So in this particular diagram, so we have a binary classification, and we have the three class classification. So we have a binary classification and we have a three class classification. Note that in the later case, we have much more degree of ambiguity. So for instance, being able to distinguish stars from diamonds may not suffice to identify either of them correctly. So since we also need to distinguish both of them from triangles. So we might see a sequence of xi and yi pairs for which yi needs to be estimated in an instantaneous online fashion. This is commonly referred to as online learning. We might observe a collection. So x is equals to x1 to so on to xm, and y1 to somewhere on ym of pairs. So xi, yi, which are then used to estimate y for a set of, so far unseen, x0 is equals to 0, 1, 2 and so on to x0, m0. So this is commonly referred to as a batch learning. So we might be allowed to know x0 already at the time of constructing the model. This is commonly referred to as transduction. So we might be allowed to choose x from the purpose of model building. This is known as active learning. So we might not have full information about x. Example, some of the coordinates of the xi might be missing, so leading to the problems of estimation with the basic variables. So the sets x and x0 might come from different data sources, leading to the problem of covariate shift corrections. So we might be given observations stemming from two problems at the